Howdy guys, Timmy D with Mid-South Drone Services here for just another video that's going to be a little different than what I've done in the past. This is going to be a remix of Dr. Stephen Medeiros from the University of Central Florida. I have linked to his videos in my previous ones. And if you are just now getting into drone mapping, one of the foundational principles that you must learn first is GNSS. So before you start trying to learn, well, how do I even go out and do surveys? How do I go out and do ground control points? How do I do PPK flights on my drone? Before you do any of that, you have to have a good understanding of the GNSS system. And so this video is a remix because his original video that he did, it was done in a conference and you couldn't really see the slides on the screen too well. And so he was kind enough to send me the slides so that I could reinsert them in the video and you could see what he was referencing to. But now he has an older video that he did where it is done on a whiteboard. He literally has got a marker, he's writing. In my opinion, that video it's gold. So when you don't know anything about satellites and GPS and GNSS, you got to watch both of these videos. I'm going to link that video down below. Again, old video on a whiteboard with a magic marker, it's gold. So much good information. And then this video was actually a little newer. I think he did this one in 2018, maybe 19, but I think it was 2018. But still, it's kind of similar to the old one, but it has some new slides, and both of these are very good. So watch these videos. They are critical to getting started in drone mapping, and then you're going to be ready to start learning about flight acquisition, going out, how to do ground control points, how to record them, how to process them, and so you'll be ready to move on to the next step. So again, thank you, Dr. Medeiros, for allowing me to kind of remix this video. Thank you for doing them in the first place. It was just so instrumental and helped me just get off the ground and get going. So here's his video. Hope you enjoy. If you like my channel, please be sure and hit subscribe. And if you want to be notified when I do new videos, hit the notification bell, and that'll let you know when I put a new one up. And hopefully moving forward, I've kind of had a time where I haven't done many videos, but I've been working on recording and doing, say, the full mapping. And I think moving forward, I will try to start breaking these down into segments. So instead of having a 30-minute, 1 hour long video, I'm going to start breaking them down into different segments. Somebody made that suggestion and I think it's valid. So anyway, thank you for being here. Hope you enjoy it.
So I am Stephen Medeiros. I'm a lecturer here in the Civil, Environmental, and Construction Engineering Department. I see some familiar faces, so some of you know me. And today I'm going to do a workshop regarding Global Navigation Satellite System and Real-Time Kinematic Surveying, so GNSS RTK surveying. So this is basically extremely high accuracy satellite positioning where it's accurate enough for us to use in land surveying applications, right, which is a highly precise and accurate field. The structure of today's talk is going to be highly geared towards hands-on application. So I'm going to go into a little bit of the theory and the sort of the electronics of how GPS and GNSS works, but mostly I'm going to focus on the practical applications of it, so that when you leave here today, you should be pretty confident that given some equipment, you could do this. Okay, so how many of you, by show of hands, are graduate students? Undergraduate students. Okay, so no professionals, which is good. Well, except one former professional. All right, so when you guys, want to contribute to your research projects, or in the undergraduate case, maybe apply to graduate school, when you get out of here today, this will be a skill that you can pretty much put to work right away. And this is the direction that the field is going, so this should make you all a little bit more highly valuable to your individual research projects if those involve making accurate field measurements. All right, so the Global Navigation Satellite System, or GNSS, is the umbrella term for many individual satellite constellations. So the most famous, at least in the US, is GPS. Everybody knows what a GPS is. So that is only one satellite constellation in the global navigation satellite system. So GPS is the satellite constellation and the positioning system operated by the United States, in particular the Department of Defense and the US Air Force. GLONASS, which also stands for Global Navigation Satellite System, is the Russian constellation. This is the next most commonly used. Following behind that is the one operated by the European Union. That one's called Galileo. Then Baidu is China's constellation. Navik, which roughly translates to sailor or navigator in both Sanskrit and Hindi, I believe. And that is the country of India's satellite constellation. And QZSS, which stands for Quasi-Zenith Satellite System, which is the Japanese constellation. Now, QZSS is one that's a little bit unique in that it's highly focused only on the island of Japan, as opposed to a global system. Now, what does the word zenith mean to you? Right? It's the highest point directly above you. Okay? So why do you think the Japanese would be particularly interested in a system that's good at zenith, meaning straight up above you? Right? Tokyo is legendary for its tall buildings that are packed very close together. Right? So if you're in one of the streets of Tokyo, it's almost impossible to see the horizon. So your satellite constellation is limited to directly above you. And this particular constellation is designed with Japanese needs in mind, meaning give you accurate position, so it has satellites that are directly overhead so that you can see them in the heart of the city. So GNSS is the umbrella term for all of these. Now, most modern GPS surveying equipment is designed to access one or more of these. So the more constellations your equipment is set up to access, usually the more expensive it is. And it doesn't necessarily flow in this direction. Some can do GPS, GLONASS, and Baidu. Some GPS, GLONASS, Galileo. Some a little bit more. And in general, and we're going to see why, this is a hardware issue. You need to have the hardware on board your equipment to, for lack of a better term, hear the signals from these satellites. That's why it's an equipment level decision, not necessarily you just need new software to hear that signal. So I'm going to phrase most of this in terms of GPS because we're in the United States right now, and this is the one I am most familiar with the inner workings of. So it is owned and operated by the United States Department of Defense, in particular the Air Force. GPS is comprised of three what we call segments. So we have the space segment, which is actually all the satellites, or in GPS terminology, those are called space vehicles, or SVs. The control segment, so these are a network of ground stations all over the Earth that are in communication with the satellites so they can receive information about the satellite's state and also update the satellite's tracking software or tracking position twice a day. Then there's the user segment. So that's us standing on the ground with our GPS receivers. And if there's one thing I want to stress numerous times throughout this little seminar, GPS functions because of highly accurate timekeeping, or the clock. Right? The clocks are the key to how any satellite navigation works. And we're going to see why in a slide or two. But I want you to keep in mind that time is crucial. We have to know when the signal left the satellite and when it hit the receiver, and that's how we compute the range. Okay, so GPS navigation and surveying is all about the clock internally. One other thing I want to point out in the user segment is that GPS receivers are what you have in your hand, right? So most of you have a smartphone in your pocket. That has a GPS receiver in it. So it's designed to hear and interpret the signals coming from the satellites. Okay, now the next generation of smartphone GPS is going to be way more accurate, but right now 3 to 5 meters is a reasonable accuracy for the GPS in your smartphone. The handheld receivers you might see from Garmin or one of Magellan or one of those companies, they can access other types of GPS with relative or differential positioning, and they can get that down to, you know, a meter or sub-meter accuracy. So it knows that you are in a cloud, a meter in diameter, with, you know, you're somewhere in that cloud of points. The GPSs we're going to use today, with real-time kinematic corrections, are accurate to within roughly 2 centimeters horizontal and 4 centimeters vertical. Right, so it knows that you're about on the face of a US quarter, the coin. So the more expensive you go, generally the more accurate you are. And we're going to talk about how we increase the accuracy for those. So as of this photo in 2015, there were 24 satellites in the GPS constellation, 21 of which were active at any given time. So there were 3 spares in orbit where if something happened to one of the satellites, you know, it was hit with space debris or failed for some other reason, one of the spares could be put into that orbit and replace the one that was broken. Now there are 32 satellites in orbit as of 2016, and 31 are active at any given time, I think. So these satellites basically orbit the entire Earth, and GPS gives full Earth coverage, so you can use it no matter where you are on the Earth. So a couple terms here. So the GPS satellites are in an orbit around the Earth, and they're looking down or sending signals down to the Earth, right? But we know that to get a position, the Earth is not a perfectly smooth surface, right? There are mountains, there are valleys, you know, the oceans are gouged out, and those are very irregular. So the Earth actually looks like this deformed ball right here. So it's very difficult to get a mathematical position from just a satellite range, considering the complexity of the Earth's topography. So how this gets addressed is by creating kind of a 2-stage system. We have a mathematical best fit model of the Earth, and then we also have a model of the Earth that roughly corresponds to mean sea level. So by the combination of those two reference surfaces, we can get our accurate position on the Earth. So one of those mathematical models is called WGS 84. I believe this is World Geodetic System, and the model was created in 1984. So this models the surface of the Earth as a ellipsoid, which is basically a sphere that is squashed in at the poles a little bit, right? So that makes sense because the Earth rotates around its axis, so we would expect a little bit of a bulge at the equator, right? And pulled in at the poles a little bit. So the major radius of this ellipsoid, right, not of the Earth, of the mathematical ellipsoid we use to describe the Earth, is about 6.4 million meters, right? And notice that this is an integer. This is an exact number. Okay, so the major radius, which would be from the center of the Earth out to the equator, is 6,378,137 meters exactly. The flattening factor is roughly 1 over 300, right? So for every 300 meters we go out from the center of the Earth towards the equator, we shrink one meter in the direction of the poles. So we can compute the minor radius as 3,356,752.3142 meters. So that's the distance from the center of the Earth to the poles. I think that should be a 6.
Yeah.
That's a I'm sorry, that's a mistake in my slide. This should be a 6 instead of yeah, because it doesn't. The radiuses don't change. The radii don't change that much, right? That would be like a frisbee. Okay. Sorry about that. This should definitely be a 6. That's just a typo. So we have this mathematical surface of the Earth, right? So from this, we can accurately position ourselves on that mathematical shell, and then we adjust that position to the actual topography of the Earth. So when we get a satellite position, it gives us coordinates in what we call geocentric or ECEF, Earth-centered, Earth-fixed coordinates. Okay? So this is a straight XYZ reference to the center of that ellipsoid shell. All right, now mathematically, the center of that shell would be extremely difficult to locate, right? It's at the direct center of the Earth. Nobody's ever been there, as far as we know. Okay, so in actuality, the center of that ellipsoid is thought to theoretically be within 2 centimeters of the true center of the Earth, right? So this is highly accurate mathematical modeling based on, probably millions of observations to get it that close. So when you get a range from the satellite, it first computes it in this geocentric coordinate system. So it's just x, y, z, right? With the origin being at the center of the Earth, the x-axis crosses the equator at where the prime meridian crosses the equator, and all the other axes are established as you see in the picture. Now, we almost never report coordinates in geocentric coordinates, ECEF, right? We want to convert this to something that's a little bit more applicable to our position on a sphere-like shape, such as the Earth. So who here has heard of latitude and longitude? Okay, so that is much more familiar. So latitude, longitude, and height are the ways we normally report positions, right? And then there are a whole series of projections that project those onto flat Cartesian planes for local mapping purposes. So latitude and longitude are both angular measures, right? They're measured in degrees, or degrees, minutes, and seconds. So your latitude is the angle from the equator up to your point on the ellipsoid. So it's latitude are concentric rings around the Earth, right? So, and that all goes by your angle up or down, north or south latitude from this equatorial plane. Your longitude is an angular measure from this meridian we call 0, or the prime meridian, from there over to your position on that ellipsoid. And then your height is computed as the distance from the central axis normal to that ellipsoid, right? So, or orthogonal or perpendicular to the ellipsoid. Sorry, I talk like an engineer sometimes. Okay, so if you drew a line that was perpendicular to that shell, it would go down and hit this vertical axis somewhere. That is your ellipsoid height. So when you get a elevation or a height from GPS, what you're actually getting is the ellipsoid height. So where you are relative to that mathematically perfect shell. That is not your true elevation with respect to a vertical datum, like, for lack of for this level of audience, mean sea level, or one of our established orthometric datums like North American Vertical Datum, NAVD 88. So your GPS receiver converts your geocentric position into what's your geodetic position, which is latitude, longitude, and height. And then I'll show you how we then further get your actual orthometric or true survey elevation from that. So how many satellites must you be in communication with in order to get a good position?
3.
What's that?
3.
3, right? So some of you have had me in class before, know the right answer to this. So if you are receiving a range from one satellite, right? All you know is that you are this far, you are X miles from that satellite. So that basically tells you you are somewhere on a sphere X miles in radius from that satellite. Not very accurate. So if you have 2 satellites, what does the shape where you can exist look like? Right? So if you took two spheres and smushed them together, the intersection of those 2 spheres would be what shape? Right? Every time you push 2 spheres together, it's going to be a circle, right? So just imagine 2 bubbles that get pushed together. The area that is common to both of them is going to be a circular line, right? Everywhere else on those 2 spheres is not on the other sphere. That make sense? So it's going to scribe out a circle, right? And this is from an oblique view so it looks like an ellipse, but two spheres together will ascribe a circle. So now you know you are somewhere on the border of this circle. Still not very accurate. So we need a third satellite, and what will be our possible position when we bring in a third satellite? So imagine taking another sphere, another range sphere, and smushing that in such that it intersects the circle made by the first two. What happens then? A point, right? Not exactly. When you cut a circle with another sphere, you're going to basically take that circle and cut across it. Now you are at one of two possible points. So you've narrowed it down now to one or two possible points. Therefore, you actually need a fourth satellite in order to distinguish you from one or the other of those points. All right, so in order to get a satellite position, you must be in communication with 4 satellites at a minimum. So the satellites, I said, broadcast a signal that gets heard by your receiver. So generally, satellites broadcast at these frequencies, at least for GPS. CA stands for the coarse acquisition code, right? This is a binary series of chirps, right? It's either on or off in a string of 1023 zeros and ones. And what this is actually, I'll talk about that in a second. Then we have the P code, which I'm not going to talk about here. And then the main two are L1 and L2. So these are the frequencies which the radio signal comes from the GPS satellites and is interpreted by your GPS receiver, right? And some of the more modern ones can also hear L5. So you notice that these are very distinct frequencies, right? They cannot be mistaken for one another, is what, they're far enough apart on the frequency spectrum such that they don't overlap and they can't be mistaken for one another. That's key. So the CA code stands for coarse acquisition code, right? And we generally call this code phase positioning. So it emits a pseudo-random noise, or a PRN number, that is 1023 bits in length. So it's basically a string of on or off signal that is either a 0 or a 1 at any given point, right? So this is 0 and then 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, all the way to, and it emits this string of numbers. Now that CA code is unique to every satellite. Each satellite has its own unique CA code. So your receiver determines from the message that comes down from the satellite which satellite that is, right? So if it's GPS satellite number 17, it knows what that CA code should be for satellite 17, right? That's part of why the hardware is set up from the beginning to hear certain signals. So it knows what satellite 17's CA code should look like at this time. So the message comes down and the receiver starts listening to it. And it hears, it leaves the signal, leaves the satellite here, and then the receiver actually tries to sync up the signal. And once it does that, it will have to offset it by a certain amount, and that offset is the time it took the signal to go from the satellite to the receiver. Right? So it knows it should be here, but it's not, it's here, so there's that much delay. And that time delay is how we compute the range to the satellite. So that electromagnetic energy leaves the satellite at the speed of light, and it takes such and such a time delay. By multiplying those, we get the distance to the satellite. So there's our first sphere. That's our first range. So we're going to do this for multiple satellites all at the same time. So this is called coarse acquisition code for a reason. Right? I believe the stated accuracy of this is about 100 meters. Right? So you're somewhere on a football field. Right? Not really accurate enough for most applications, but it is really accurate enough for you to determine which satellites are above your head. The more modern way to do this is with carrier phase positioning. So the carrier phase is that L1 and L2 signal, right? So it's actually a modulated signal that comes from the satellite down to the receiver. So that same delay happens, except this time let's say it leaves the satellite at the green one, and then it arrives at your receiver as the red one. Okay, so there is some phase difference between those two signals, right? So you would have to shift the phase by some delay in order to sync up where it should be based on your receiver. Okay? Now, do any of you see a problem with this or a difficulty interpreting?
Yeah, you don't know which crest matches up with the other crest.
Exactly. Okay, so if you were to range based on just this difference, right, it would be in the like fractions of a millimeter. That would be how far it thinks you are from the satellite, right? Because the wavelengths of these, if you're off by one wavelength, that is, you know, they're very short wavelengths. I think L1 was on the order of like 1,500 megahertz, right? So that's a million times a second it's passing through. So very short wavelength. So what we have is a number of wavelengths that also are included in the delay, but we can't quite tell from just the phase difference. Okay? So that number of full wavelengths is called the integer ambiguity, because it is an integer number plus the phase difference gives you the total delay that you can then compute the range with. All right? Any questions on that? So resolving this integer ambiguity is the crux of highly accurate GPS positioning. So ways we resolve that integer ambiguity are using multiple satellites at multiple times and on multiple frequencies. So if your receiver can hear L1 and L2, now you have many more data points to figure out how many wavelengths, how many whole wavelengths plus the phase difference you're observing are there. Okay, now this is highly mathematical process. It involves the procedure is generally called differencing. So there's single differencing, double differencing, triple differencing. So you're looking at satellites from one point, right, multiple satellites, and then as they move in time, you can then take another reading, and as they move in time, you take another reading, and the more readings you take, the integer ambiguity becomes clearer. Right? The more information you get a progressively better guess at that integer ambiguity until you solve it. Okay, so it generally works out to be a system of equations that, with more information, eventually you converge and you're able to solve that linear system of equations exactly for the integer ambiguity. That's why when you turn on your GPS, you don't have a position right away. It has to warm up, we call it. So it has to figure out what satellites are overhead, get their course acquisition codes, figure all that out, and then it starts to do the integer ambiguity calculations until it gets solved. So in practice, we generally, so I'm going to shift now from space now back down onto the ground. So in practice, we generally use GPS surveying in two modes, static and kinematic. So static means we set up a GPS receiver on a point and we leave it there for an extended period of time, right? Usually a minimum of 2 hours. So we make a highly stable GPS occupation, we call them. Sometimes you can actually see my fixed height tripod over there. And we'll actually stabilize the legs with sandbags, put cones around them so nobody bumps into the tripod, because we want to have that GPS receiver absolutely still for a minimum of 2 hours. Now, there's also a mode called rapid static that uses a different algorithm to compute a position, and that needs a minimum of 15 minutes of continuous data. So what happens, and I want to go back to the clock aspect, right? Not only is the synchronization of the clocks and the difference in the clock on the satellite and on the receiver extremely important. In fact, one of the updates that these satellites get from the ground station is the clock bias correction. Right, so the clock on the ground station updates the satellite clock because that can get, have some error in it or some bias in it, and that is non-stationary. It changes over time, so that's why it gets updated twice a day. Basically, the clock gets repaired twice a day. So imagine, how accurate your watch would be if it got fixed by the best people in the world twice a day, right? So The other aspect is the longer you collect data, the more accurate your position will become. Okay, so that generally looks here, like this little diagram here. So here's latitude and longitude, right? Obviously, it's projected onto a two-dimensional surface or a Cartesian surface. So when you start collecting data, you might pick up this point, right? So say you're collecting data once per second, so a 1 hertz rate. You'll start getting points every second. You'll add another point to your history. And over time, you'll get a point that's the mean of all those points. So the more points you collect, right, the more accurate your mean will be. The closest to your true position it will be. So remember, accuracy is the distance of your measured position to your true position. Precision is precision would be how tightly clustered these points are. That would be precise. And accurate would be how close, it's tough to see on this screen, but there's a black dot in the center, how close that is to the true position. So static surveying, we occupy that point for a long time, and then we submit that long record of observations to a positioning service. Now there are at least half a dozen of these globally. In the US, we use the National Geodetic Service, OPUS, Online Positioning User Service. So this is a federal agency that has a vast network all over North America of stations that have both a fixed position and are continuously recording GPS data. Right? So these are called CORS, C-O-R-S, or continuously operating reference stations. So these stations have a fixed position that is known, a true position, and they are receiving signals from a satellite, so they know the current error in the satellite signal for that location. Now these are spread all over, so they can interpolate that error all over the country and basically form a interpolation surface that factors in all kinds of things such as space weather, atmospheric distortion. You know, all these types of things get factored into NGS's model. So you submit your observations over an extended period of time, and it basically goes back to its model and says, okay, during that time at this location, that position needs to be corrected like as follows. So it goes through all its algorithms and then emails you back a highly accurate position report. And that's usually accurate to within millimeters, right? Or sometimes even sub-millimeter accuracy. So you are right on that point. So typically we use this to establish benchmarks, say for a construction site it's a little bit different to do traditional surveying to get to this point. So we'll use static surveying to establish a local benchmark. Now I do not mean a geodetic benchmark, one that other land surveyors will reference. This is sort of, although some people say that eventually, you know, static surveying will be, you know, used to do geodetic benchmarks. Sorry. However, if you wanted to take the topography of a whole construction site in order to, you know, do the grading design, for example, you're not going to sit on each point for 2 hours, right? That would take an eternity to do, and in fact would be slower than traditional land surveying. So there's another method called kinematic surveying. Oh, that really didn't come out. So this is my graduate student Paige holding a GPS receiver, and this is my former graduate student Kareem also doing this in the Apalachicola Bay region in Florida. So kinematic surveying uses a differential positioning technique. So differential positioning is when you use a station that has a known position as a reference point to help you resolve the integer ambiguity and get a more accurate position where you actually are. So any differential system has a base station that continually broadcasts its position. And then we have another GPS unit. Generally this is called the base and this is called the rover. So the rover is the one that actually moves around. So this station broadcasts its GPS position to the rover. The rover can compute a vector from the base to the rover. So now you have a satellite position and a distance from a known point. So that allows you to get a much more accurate position. Now, there's a term called differential GPS, or DGPS. That is this same concept, but only using the CA code. right? So the time delay from the course acquisition code. Generally, what's thought of as RTK, or real-time kinematic, does this, but with the carrier phase positioning that I talked about earlier. Okay? So that's the difference between DGPS and RTK. So RTK generally uses a fixed position that either you set up yourself, right? So you can actually go set up your base station on a known point. So a lot of times for research purposes, since I'm frequently out in the middle of nowhere, I will do static surveying on a fixed point that either I set as like a nail in the pavement or a nail in a sidewalk, or sometimes, you know, driving a piece of steel rebar into the ground. I will set up and do a static occupation on that fixed point, knowing that I'm going to come back the next day and use that as my base station. So I'm going to set up a base station right on top of that point, locally on site, and that base station is going to be turned on. It's going to be getting its GPS position and then simultaneously broadcasting its position out to the rover. So we can do the same differential GPS that I just showed, but I'm controlling the base station. Right? So this is what we do when certain site conditions exist. However, there's a proliferation of both paid and free, what we call real-time networks. So these are networks managed by a third party that have, again, a series of those continuously operating reference stations. So these reference stations know their position, and they know the GPS position that they're getting. So they actually upload their position to what's called it's basically a server, but we call that a broadcaster. So the receiver talks to the broadcaster, and the broadcaster sends its position out to the internet. And the rover now does not need a base station set up on site, it just needs access to the internet somehow. So the rover accesses the internet via cellular modem, connects to the broadcaster, and then receives the positions that way. So this is much, much easier than actually setting up your own base station for many reasons. One, it's network RTK is basically just turn your machine on and go. Right? It's very, very simple. Second, the network is it's a network of multiple stations. So it can actually interpolate positions between the stations, and that's called VRS, or virtual reference station. So it almost gives you your own little reference station that's just interpolated from all of its permanent stations to your position. So again, you access this usually via cellular modem, and this could be a variety of ways. You can actually have a SIM card in your data collector, or in some of the older equipment, actually in the receiver. So my rugged tablet that we're going to be using today, that has a SIM card that goes right in it to access the internet. Also, I have a few Wi-Fi hotspots that I keep with multiple carriers. You know, I have a T-Mobile, an AT&T, and a Verizon one. So then I just use the Wi-Fi in the data collector to connect to the internet. Or sometimes in a pinch, I just turn my phone into a Wi-Fi hotspot to get me onto the internet. Now, this can only be done where? Where you have cell coverage, right? And usually you need very, very good and stable cell coverage. And you would be a little bit, at least I was a little bit shocked at some areas that don't have cell coverage that's good enough to do this. Right? If it goes in and out, like if you keep losing your connection to the network, that's very bad. Right? You're going to get generally bad results from that. So I actually wrote a blog post about buying a SIM card for this purpose, and it's basically the end result of many, many headaches and many hours sitting in a cell phone store with people who are very good at their jobs but have no idea what you're talking about. So I actually wrote a little guide to, speed this process up for you should you have to do that. So this is the Florida Permanent Reference Network. This is freely available, and it's operated by the Florida Department of Transportation. So you see, this is that network of stations I was talking about. Right? So all these dots are stations, and their color indicates their status. So all the green dots are active. All the red dots are down for some reason. And then all the yellow dots are, I believe, have some sort of anomaly, but they are operational. So this is just basically a live updating map. Yeah, see, it's called low faith. So like for some reason the network has low faith in that particular signal. So when you're preparing to go out and do one of these surveys, it all begins in the office before you leave, right? Preparation for this type of surveying will make your life a lot easier and a lot less stress. So you should definitely look at where you're going, right? Open up Google Maps or GIS and find out where you're going. Download the benchmark shapefile and see if there are any usable marks near you that you can just put your base station on and use. Otherwise, you might have to set one up yourself, right? Are there other known points there based on maybe previous work you've done or other benchmarks that you can actually do a procedure we call checking in? So when you're doing, let's say, network RTK, it's good to know where the benchmarks are because you can go over and get a position on that known point and then compare your measured position to the known position, and that can help you adjust your data afterward. You have to make sure you have the right geoid model. So what I talked about earlier with the ellipsoid model, and I'll show a diagram of this in a second, the ellipsoid model is the perfect mathematical representation of the Earth. The geoid model factors in the undulation of the topography. So you actually calculate your survey elevation based on the geoid model and the ellipsoid model. Now, these days, most of the geoid models are in a binary computer format, meaning that you can cover the entire North America in one file. Right? It's a binary file. It has the entire geoid model that your data collector can understand for a big region like all of North America. There's also a text version of this, and all of North America would not fit on your data collector. So previously, we had to actually go into a piece of software and select a small section of the geoid model to download onto or upload onto the data collector so that we could use it. So we had to kind of know where we were going, clip out some of the geoid model, and then upload that onto the data collector for use in the software. If we did not have a geoid model on the data collector that the software in the data collector could understand, you would only be getting ellipsoid heights in the field, which are not that useful. You know, normally we're trying to get topographic elevations relative to a datum. And then, so once you have these, and there are, you know, maybe a few more steps in here, but this is the key stuff. You must, you know, always check your equipment and know the status of your equipment. I suggest you do this personally, right? You never want to rely on a graduate student unless you absolutely have to, right? So make sure the batteries are charged, right? There is nothing worse than getting out there and finding your batteries are dead. Now, this is not a night before thing. This is a couple days before thing because, you know, we really, or if you're surveying a lot, you really beat on batteries. You're constantly charging them up, discharging them. I mean, it's a very rigorous life for a GPS battery. So they can fail. And you don't want to put them on the charger the night before and then get there and find that, you know, 2 out of your 6 batteries have failed. Because that could really, you know, ruin your day or limit the amount of work you're able to do. And these batteries, you can't just go to Best Buy and buy them. Right? Normally you have to get them from a surveying manufacturer, a surveying retailer. Make sure your software and your firmware is updated. So you should have the latest updates on your data collector software. Your data collector should have all of its firmware, and even more important, your GPS receiver should have its most updated firmware. So either get on the mailing list for your receiver so you know when all the firmware comes out and update it. Right? So the firmware is actually what gets put onto the internal electronics of the receiver. And if you don't have the right firmware, you could be making errors in satellite tracking and all of these things that get corrected over time. So you have to make sure your firmware is updated on your receiver. You should also know what firmware is on your receiver at any given time. That should go in your field notes. That way, if there's an update that comes out, you may be able to go back and, you know, the manufacturer might say that if you're using this version of the firmware, you know, there was an error, it looks like this, here's how you correct for it, or that version of the firmware contained a huge error if you were connecting to GLONASS you have to scrap all that data, right? So it's important to know which firmware you had at that time. Check all your screws, right? Replace any worn parts. Again, these are all things you do not want to happen in the field. This one has burned me a couple times, right? Normally, since I only do this type of work a couple of times a year, usually, it's that my prepaid SIM cards have expired, so that like that phone number doesn't work anymore, and then I can't access the internet while I'm out there. So make sure that your cellular modem and connections are all up to snuff. Everything's got money in it and can be used. And all of these network permanent reference networks that I mentioned, they all have logins and passwords. So you need to create an account. Usually those accounts are per device, not per person. So if you have 4 GPSs, you need to create an account for each one of those, because they have to access, only one device can be on accessing the network at one time per account. So if you have 3 GPSs, you need 3 accounts to attach to it. At least that's the case with the Florida Permanent Reference Network. And make sure that have tested it and know that you can connect to the network if necessary. So these are all things you should do before you get there. Right? You haven't even left the office yet. So back to the GPS heights. Okay, since I mentioned it in the previous slide, this is the diagram that we use. So you see that the ellipsoid, right, is nice and smooth, right? That's our mathematically perfect model. So from the GPS, we get little h. So it knows how far you are from that ellipsoid, and you can be either above it or below it. Okay, so it can be positive or negative. N is the distance between the ellipsoid and the geoid at your position. So this is the geoid model you downloaded onto your data collector, right? It basically contains information such that your data collector can compare the two surfaces. So then the data collector computes an n. And your actual height, since that's referenced to the geoid, right? This would be NADD88 or mean sea level or something to that effect. It is h is equal to your ellipsoid height minus your geoid height, we call it. Okay? So this would be positive, say 20 meters, minus negative 13 meters would be a height of 33 meters. Right? So see, the geoid model is below the ellipsoid model. So this would be a negative geoid height at this point. And again, you see that this varies spatially. That's why you need 2 surface models to do these computations. Now the geoid is being constantly improved and updated, right? In fact, local reference networks are now producing geoids for their reference network, right? Because and generally in positioning, the smaller you get, the more accurate you're going to be, right? Just imagine if you project a sphere onto a Cartesian plane, it's only perfectly accurate at one point, right? The orthogonal vector from the surface of the sphere onto the point. Everything else is a little bit warped as you get further away from the center. So the more local you can be, the better. So the geoid also must match the horizontal datum that you're using. Right? So right now, the most up-to-date one is Geoid 2012B, or we just call it Geoid 12B. Right? So there was a Geoid 12A, now there's a Geoid 12B. In order to use that geoid in North America, you must be using the North American datum of 1983, the version that was updated in 2011. Those two, the vertical and horizontal datums go together. Right? So if you've ever looked at a data collector or done any work in GIS, when you go to projection, you get a menu that's a mile long. Right? There are projections, just in North America, there are tons of projections to use. So there's a broad array of choices. You must ensure that your horizontal and vertical datums are the same. Right? So if you're using Geoid 12B, you must be using NAD 83 2011. I know it can be a little bit confusing, but a quick Google search, or even better, talk with somebody who knows about this stuff, and you will be all squared away. So when we get to the field, right? So we're actually going to go out and make some measurements here out in the Arboretum in a second. When you're in the field and you have to set up your base station, the very most important thing is the position of that base station. You must set it up on a known mark where you have like a position written down. So perhaps I did a static occupation on that position, and now I have an OPUS report, and I'm going to put in the latitude, longitude, and ellipsoid height of that position. You also must measure the antenna height as accurately as possible. Right? So the antenna height is the distance between the GPS receiver and the mark. So these are both, this is a 2-meter rover pole or 2-meter rod, and that is a 2-meter fixed height tripod. So from the tip of that spike to the plate on top is exactly 2 meters calibrated. All right? However, even though that's calibrated, I still measure it with a tape each time. Just to make sure, you know, if the point on the screw is a little loose, right, that can extend it just a little bit. And I can't stress enough, have the most accurate as possible antenna heights. So again, you can set a mark, do a static occupation, submit it to OPUS, right? If you don't have that kind of time, you can set a mark, perform a rapid static occupation, so 15 minutes or a little bit longer than 15 minutes, submit it to OPUS. OPUS says you'll get a response within 24 hours, but usually it's a little bit quicker than that, depending on how many other people are doing that same operation at the same time. Right? So you kind of go into a cloud computing queue for that to happen. You can also read from GPS. So if you have no idea where you are, you can tell when the base station configuration asks you for its position, you can read that from GPS. So once again, the clock. The longer you read that position, the more accurate it's going to be. So you can read GPS for approximately 15 minutes and get very decent accuracy when you need to. This is definitely in order of preference. Right? I definitely prefer to set up on a mark where I have a millimeter precision position on it. Then make sure you secure your equipment. Right? Theft of GPS equipment is very common. It's very expensive stuff, and GPS can be used all over the world, right? So it's not difficult for someone to steal your equipment and ship it to another country where it's less likely to be discovered, all right? And this actually happens, right? So they'll just move your equipment somewhere else and, you know, start using it. So make sure you secure it, and like I said, protect your base station from foot traffic. Make sure nobody walks by and kicks the base station, because that will really mess up your day. One thing I didn't put on here that I probably should have is make sure your base station has sufficient power to maintain its, to be up during your entire field mission. Right? So if you're going to be out in the field for 8 hours, you need to make sure your base station is going to be running for 8 hours. Now most of these base stations, you can actually hook up an external 12-volt battery. So just like, you know, the battery in your car is a 12-volt battery. So you can, you know, buy a battery and leave it at the bottom and hook it up to that. That's also usable. One time I actually had to pull my truck right up to the tripod and hook it up to the battery in my truck because I forgot to charge the batteries, and I needed that base station up, and I had to put every battery I had into the 2 Rovers I had. So nobody's immune from these kind of mistakes. Next, you must configure your base station. So how the base station communicates with the rover is usually through UHF radio. So that's just an over-the-air radio wave. There are, I know Topcon, Sokia, and Carlson both have a system now where you can communicate with your own base station using an internet protocol. Right? Some of them, they all have names like Relay or TalkTalk or, you know, something like this. So you can actually use the internet to communicate with the base station that's 10 feet from you. But most of the time you're going to be using UHF radio. So you're going to specify a frequency, a broadcast frequency at the base station, and you should have a device that allows you to check if that frequency is clear of voice traffic. Right? So, you know, a lot of places sell these little walkie-talkies where you can just punch in and listen. And if there's, you know, there's nobody on your frequency, that's probably a safe one to use. Follow the manufacturer's guidelines and workflows. One thing the GPS or GNSS surveying industry does well is every manufacturer puts out these highly detailed workflows on basically step-by-step, screen-by-screen, how to configure all your equipment. Follow those, you know, extremely closely. Don't deviate from them under any circumstances because they have done this over time and they know what works and what doesn't. Always, always, always confirm the projection and units you're going to be recording data in. Okay, so this is highly important if you want to use your data when you're done, right? Which is almost always the case. And lastly, the moment you get to the site, get your batteries in and get your GPSs on. Like I said, it takes time to acquire satellites to lock and resolve that integer ambiguity. The sooner you get your GPSs on, the faster that's going to happen. Okay, now, I mean, we're getting very, very fast lock times now as the technology has progressed, but this is still a good practice, right? I take them right out of the case, batteries, turn them on, and then I just keep them in a safe location until I'm ready to mount them on the equipment and configure them. If you're on the network, some of this stuff still applies. First of all, accurate antenna height. So both the base station and your rover need to have accurate antenna heights. When you configure, the general direction is to use the data collector Wi-Fi now rather than a SIM card in the data collector. So most people are carrying Wi-Fi hotspots and using the data collector Wi-Fi to get corrections, to access the internet to get their corrections. So make sure you have a solid signal for that. Make sure your connection to the network is steady. So that's both the connection to the cellular network and the connection to the reference network. So make sure that whole pipeline is solid. Again, follow the manufacturer's guidelines and workflows. They'll probably have a completely separate manual for using a network or using a base station. Again, confirm your projection in units and turn your GPSs on as soon as you can. So when you're actually doing the survey, now everything's configured and you're out there, you're collecting points. Keep an eye on the diagnostics that you're getting on your data collector. So your DOP values, or dilution of precision. So these are values that are basically environmental factors that can reduce the precision of your measurements. So there are accepted values for DOPs, and there's a horizontal DOP, a vertical DOP, a positional PDOP, and there are a couple other ones. Also, your standard deviations. So you'll notice that your position, like I said when I showed you that little point cloud, right? You're getting multiple positions, so you can actually compute a running standard deviation. So you want that standard deviation to be as small as possible, right? Which means you're as precise as possible, right? Your distribution of possible locations is very tight. So you want to monitor that and make sure you're within the tolerances that you have set. Now, when you're actually doing RTK surveying, your data collector will show you that you are in one of three modes. The first mode is autonomous, right? All this is saying is that you are a standalone GPS. You're just a person with a GPS. You're not receiving any corrections, or there's no communication with the network or the base. So you're getting standalone GPS accuracy, and that can vary, but usually the 3 to 5 meter rule of thumb is what you have for autonomous positioning, right? So autonomous means you're on your own. Float is the second mode, right? So you'll go from autonomous, and then you'll see it shift, and it'll actually say float. So float means that you are talking with the base, but you may not have enough satellites in common yet such that the integer ambiguity is not completely resolved. So it's still trying to figure out how many full wavelengths to add to that fractional phase difference at the end. So a lot of times it's called float because you might have like 6,372.812. So you have that floating point number. It hasn't yet decided which integer to use yet. So float accuracies can generally be sub-meter, but again, you only want to start surveying when you are under fixed mode. And normally all the software has a very, very pleasant ding sound when you switch into fixed. So you'll be in float and then you'll hear that very happy like ding, and that means you are now fixed. So you have the integer ambiguity is resolved, you have good communication with the base, and you'll notice that your standard deviation will drop, and then here it'll drop to, if you're surveying in meters, it'll be 0.011 or something to that effect. And then general heuristic or rule of thumb is your vertical will always be half as accurate or half as precise as your horizontal, just because we can't have a GPS satellite on the other side of Earth to help us resolve the vertical position. So that's why it's generally about half as precise. So fixed is good. Everything is locked in and you are ready to get points. Most data collectors are set by default to only store fixed points. So it'll refuse to let you, it'll say your standard deviations are too high, and it'll say did not store the point. So when you, I'll actually just bring this over. So when we get out there, you'll see that there is a bullseye level on the rod. So for that, we want to hold the survey rod, right, which is going to have a big antenna on the top of it, such that that bubble remains in the center of the bullseye. Now, if you're moving quickly, you might not have this bipod set up, so you'll just be holding it steady. Now, if you're not holding it steady, what are you doing to those standard deviations? Right, you're actually increasing them, right? Because when you move over here, you get a position, and you move over here, you get a position, and here, and here. So you're actually artificially increasing those standard deviations. So that might cause some points to be rejected. So you kind of, the more you do it, you get better at holding it as still as possible right there. If you somehow can't do that, then you can actually stabilize it with the bipod such that the bubble's in the middle, and then you store your point when it's absolutely still. Typically, we store 6 to 10 points per location. So I'll go here and I'll press survey, and the software will collect 1 point a second, and then it'll show me point stored, and then I can move on. I generally don't use a bipod if I'm going to be either moving quickly, or a lot of the work I do is in coastal salt marshes, so very, very dense grass, and the bipod would never be able to find a spot to hit. And if it did, it would be really soft. So, bipod is optional, but highly recommended if you need it steady. Also, the bottom of the rod. If you're surveying hard surfaces, right, you see how that's a point? That is ideal for hard surfaces. However, for soft surfaces, you might actually penetrate the ground. So therefore, you're getting an elevation that's a little bit too low, right? In a coastal salt marsh where I do a lot of my work, you would be just the weight of the rod alone would sink that thing in a couple of inches. So you have a point. You also have a topo shoe, which is basically the same diameter as the rod, but just has a flat bottom on it. And then you have an extra wide topo shoe, which is the same diameter, but it has a plate on the bottom of it that's a couple of 2 or 3 inches in diameter, and that's for really soft surfaces, right? So consider that, and if you, for example, have to use a point on the ground, just be conscious of the fact that you don't want to shove that point all the way in, right? Keep it slightly above, or don't let it penetrate. So here are some final tips as to what you should do. First of all, I cannot recommend this enough. Make checklists, right? Have a checklist for office prep, have a checklist for when you get to the site, have a checklist for when you leave the site, and have one for when you get back to the office and are post-processing your data, right? Leave some white space on your checklist so that you can learn from your mistakes, right? Oh, we should have done this. You write that in, and then you update your checklist, okay? After, always debrief. Sometimes it's just a conversation on the way home, right, in the truck. Hey, that didn't work out. We got to change that. What do you think? Okay. Always talk about it, and then ask a lot of questions. I find that the surveying community in general is pretty cooperative. They're, as long as you're respectful, I've gotten great advice from, internet forums, and especially from the manufacturers. So they are, there to help you, and absolutely you should use that as a resource. So that's it for the classroom portion of this. A lot of the material, including a lot of the images, I derived from this textbook. This is the textbook that I use in the Civil Engineering Measurements course. And here is NGS's website, ngs.noaa.gov. That one's pretty easy. And the Florida Permanent Reference Network is, again, at this website right here, FDOT's website. So are there any questions before we get our hands on the equipment? All right, so let's get the stuff up and running, and we'll go outside and we'll actually configure the base station, configure the rover, and take turns collecting some points. Thank you very much for the opportunity. One thing about GPS is you always want the clearest possible view of the sky. Right, so this actually is, I would consider it to be a less than ideal spot for the base station, just because, you know, we got a building there, so that's taken out a big chunk of our horizon, and then you know, these trees will be somewhat difficult too. Normally, what we do is we actually set the data collector so that we mask out usually between 10 to 15 degrees of the horizon, because the satellites that are in that zone have to pass through the most possible atmosphere to get to us, and atmosphere equals dilution of precision, generally. So we want to avoid that. So, Mr. Spearing, how about right there? Okay. So this is a 2-meter fixed height tripod. So meaning that from the top of the plate down to the spike is 2 meters. So 2 of these are operated with hand clamps, right? So I can't hold it. If I squeeze, I can. So who wants to try leveling this thing? Anybody?
Go ahead, Chimney.
So when you set up a fixed height tripod, Ali, will you open up the GPS case? It has a bullseye level, just like the Rover pole does, except this one obviously has 3 legs and that one only has 2. So when you set it up, one of these legs is held by a screw, the other 2 held by hand clamps. Always make sure this screw is loose, right, at first while we're leveling. Okay? Yeah, go ahead and... Nope. So this is the GPS receiver we're going to use as the base station. All right, so when we take this stuff down, you know, we can take a look at it. So I'm just going to attach this to the top. So it just screws on there with a standard survey thread. And this is just an antenna for the UHF broadcast of the corrections. And again, I'm just going to turn it on so that we start acquiring satellites right away. And Ali, you can turn the other one on. There's a power button on the front. Press and hold that. All right, so Shiblu now is going to set this up. So he's going to grab both of these, and see this grip right here? Yeah, you want to squeeze that hard, or somewhat hard, and then slide it around such that you, yeah, make sure you're always squeezing when you're moving. So squeeze as hard as you can, and then try to get that bubble into the center of it. Yeah, it's kind of like a game. It's pretty fun. And then when you're in there, you just let go.
Almost.
Yeah. Now gently let go. I could not have done that any better myself. That was a really good job. Okay, so now the base station is plumb and level. So now we're gonna set up the rover and then configure the base station. So go ahead and screw that onto the top. So the standard survey thread is 5/8 diameter by 11 threads per inch. And that's pretty common amongst all survey equipment to allow interoperability. Yeah, so screw it on. Yeah. All right, so I'm going to use my data collector here to configure both the base station and the rover. So we don't see any wires here. How do you think the data collector is going to communicate with these two GPS receivers? Bluetooth, right? Wi-Fi, not a bad guess, right? But we're going to establish Bluetooth connections between these two. So I'm just powering on the data collector, and this is actually, most data collectors run Windows Mobile operating system. This is actually just a small, rugged tablet computer, so this one's actually running Windows 10. So it's you know, a little bit more powerful, but you know, data collectors often run, you know, their own, or if it's a data collector made by a particular manufacturer, it'll run their own proprietary operating system that really only does this. So the software I'm using is called ServPC. It's basically a software by a company called Carlson. They make survey software and survey hardware. ServCE is one of the software packages that is generally used by all types of GPS receivers, right? A lot of the other data collector software can only be used with that brand of GPS receiver, right? So there are many, Trimble, Topcon, Sokia, Leica, they all make excellent equipment. So just make sure that your data collector is compatible with your receiver. ServCE is generally compatible with every receiver, which is why I chose it to teach with, because a lot of times we get donated equipment and I want to have the most flexible possible system to use. So most data collectors are just a touch screen or a combination of a touch screen and a numeric keypad. So the first thing we do is we create a surveying job, right? And that's basically the master file that contains all of the observations and other information about, you know, which satellites we were connected to and all these other stuff. And typically that's a group of files, not just one file. So I set up my projection and the units I'm going to use. That's very important. Like, you must know that you collected your data in feet or meters, because then when you try to upload it to GIS or something, you know, you want that to be consistent. So I'm going to establish a Bluetooth connection with the base. So on the base, there's on the GPS receiver, there's a series of diagnostic lights. So I just heard it beep, so there's definitely a blue light blinking on that, and that says that we have a solid GPS connection. So the first thing we do is we specify the manufacturer and the model of the GPS receiver, okay? Because the distance that we know for antenna height is from the point up to the bottom of this plate. The actual antenna is located inside this little dome at the top, right? Or, you know, various antennae are set up different ways. So that antenna actually has a phase center, which is where the actual vertical measurement is taken. So the software, in order to be compatible, in order to support this type of receiver, the manufacturer sends Carlson, you know, its phase center information. So it knows that it's about, you know, 80 or so millimeters from the base up to the phase center of the antenna. So it makes that adjustment inside the software. So the Bluetooth is connected. Now I'm setting the antenna height. It's 2 meters or 6.5617 feet. This is where you specify the elevation mask. So I want to discard every satellite within 10 degrees of horizontal, right? So I'm eliminating the satellites that are highly probable to have a lot of atmospheric interference. And then the key part of this is setting up the RTK connection. All right, so I'm setting up this base station to use UHF radio to broadcast to the Rover. Ali, can you grab me another antenna from the case? Yes. So I'm setting this up to broadcast via UHF. So these are Hemisphere S320 receivers. So these use a internal NL400 microHard UHF radio. So I also must specify the frequency, right? So I'm gonna not take my own advice and not check this frequency for voice traffic. right? But I'm gonna broadcast on 445.45 megahertz, right? So that's the frequency I'm gonna use for this. That one's generally open. And I can also set the power. The maximum power is 1 watt, right? As you increase power, you actually need an FCC license, so a Federal Communications Commission license, to broadcast at that power on some of these frequencies. So since I don't, I must keep it as local as possible. So you always want to use the smallest amount of power that you need to do the broadcasting. That'll save battery and other stuff. There's also different types of messages that contain the information being sent from the base station. So these are just a variety of formats. One is called RTCM, one's called CMR, and there are a couple older ones that aren't used as much anymore. But RTCM version 2, RTCM version 3, and then CMR, and then there are a series of modified CMRs that are manufacturer specific. So you must make sure that your base and receiver are both operating on the same frequency with the same message type, right? So once that's configured, I'm gonna add a whip antenna to the Rover so it can hear the UHF signal sent by the base station. So now the software is asking me to tell it the position of the base station. Right? It wants to know where the base station is, so I have 3 options: read from GPS, enter the lat long, or enter the grid system coordinates. Right? So grid system would be a projection, not lat and long. So since I just set this up for demonstration purposes, I'm going to read from GPS. It gives me the option to enter if I want to do it by number or by time. So I'm just going to take 10 readings just so we can keep things moving. But again, we'd want to do at least 15 minutes if this were a real project. Actually, if this were a real project, we'd want to set it up on a known point. So now it's collecting readings 1 per second. 5, 6, 7, 8, 9. And I have a root mean square error of about 6 feet horizontally and about 11 feet vertically. Right? It was showing me that. So it also allows you to set a base ID. So you can give this base a number between 0 and 4,000 usually that identifies this base. So if you're on a big construction site where you might have different companies using RTK at the same time, you want to make sure your base is identifiable from everybody else's base. So you might want to give it a unique ID. You can also save the base station settings to a file. So if you set up the base on a known point, you can do all the configuration and then save those configurations to a file, which then next time you just load that file and you don't have to go through it all again. Alright, so the base station is now set up. It's reading GPS from the satellite and broadcasting its position over the UHF radio. However, nothing is listening yet. Now I have to configure the Rover. So again, I specify the manufacturer. Actually, the base station and Rover setups are very similar. Specify Bluetooth communication, right? And I always walk around and look, so you can see here that the Bluetooth light is blinking blue. That means we're in communication. Again, I would measure the antenna height, right? And there are actually 2 ways to measure the antenna height: vertical and slant. Vertical is if you know the plumb vertical distance from the bottom of your receiver to the mark, right? In this case, this is a fixed 2-meter pole, so I can tell it it's 2 meters vertical. If I actually had to measure this, right, I'd want to do a slant measurement. So a slant measurement, Ali, can you grab me the measuring tape? If you choose to enter the measurement as slant, it knows that this particular make and model of GPS is going to be measured from these 2 points right here. These are called the measuring points, or some people refer to them as the ears of the GPS. So that has a place where you can hook in your measuring tape and actually measure all the way down to the point the exact antenna height. And you notice it's called slant because we're kind of measuring at a slant from out here down to the tip of the point. So when you enter a slant measurement, it uses the preloaded specifications of this particular receiver to adjust that height to exactly what it should be. So I'm going to leave it as 2 meters vertical. And now I'm going to configure the RTK. So since these two are identical receivers, either one of these could be used as the base of Rover. So I want to use the same internal NL400 microhard radio, right? So that's just the UHF radio associated with this particular model of GPS. And I want to configure the radio to make sure that it's listening on the same frequency and the same message type. Now, a lot of times when you set up the Rover, they've said, they've defaulted the message type to any. So as long as your base ID matches up, the Rover figures out what the message is. So it's kind of taken one configuration step out of it. So I click the ever-present green check mark, and now I'm ready to survey. So in ServCE and ServPC are essentially the same software. One's designed to run on Windows Mobile, one's designed to run on Windows 10. So I kind of still say ServCE even though I'm using ServPC. So in ServCE, you go to store points, and that basically gives you a map and allows you to start collecting points. Now, unfortunately, or fortunately, I can't show you autonomous, float, and fixed because I'm already fixed, right? So this is, relatively good GPS conditions. Okay, so now I have a standard deviation of 0.012 feet horizontally, so 12 1,000ths of a foot horizontally, and 0.031 vertical. I have a position dilution of precision of 2.22, right? Typically, I've heard that you want that to be less than 6. I've also heard that you want it to be less than 4. I don't think I've ever heard it you want it to be less than 2, but typically around 2 is what you get for your PDOT, we call it. And it's giving me my northing and easting and my actual orthometric elevation, right? So my survey elevation above the data, because there's already a Geoid model put in here from what I did in the office. All right, so let's collect some points. So who wants to go first? I'm gonna fold these down, and so we're just gonna hold it while we collect these points. All right, I'm just gonna hold them down and Velcro it in, and so we can move pretty quick and everybody can get a chance to do it. All right. So up at the top here, we have 4 letters, SAOC. S stands for survey or store point. That's the one we press when we're ready to actually store the point. So the objective here is to get on the point, and for the purposes of this demonstration, don't necessarily worry about the penetration of the spike into the ground, right? Just take a point and just be cognizant that if you were doing this for real, you'd want to have a topo shoe on there if you were in a grassy area. So you want to get the bubble right in the center of the bullseye, and then click store and try to hold it as still as possible. And you hear that happy sound? That means the point is stored, and I have this set up today to show some diagnostic information. So this is telling me that I got 6 out of 6 valid readings. So I set it up to collect 6 points. All 6 of those had standard deviations that met my criteria. They were all taken under a fixed mode, and it gives me my position, right? So we're at elevation roughly 69.781 feet right now. Then I click the check mark, and I get another happy sound that stores the point. And now that point is displayed on my screen, okay? So, Shiblu, give it a shot. Okay, so take it, put it on any point you find interesting, that one will do. All right, so what I do is I hold the rod with my left hand, and then, actually, you know what? You should probably use the bipod. This is you're doing this for the first time, so let me kick these out. And since you did the other one, this should be similar for you, except this time you're adjusting with your thumbs. Right? So you want to squeeze those, drop the legs. I'm sorry, try to get a big base. Right, squeeze the buttons. There you go. See, these drop out. And then now squeeze the buttons and shift it around until your bubble's in the center. So you want to push it that? Yeah, there you go. Make sure you're always squeezing. Otherwise you'll pick the legs up, and that's no good. That's good enough. All right, it's a good way to work on your grip strength. Okay, now when you're ready, tap the S button with the stylus or your finger. So you see now it's reading 1 of 6, 2 of 6, and it's telling you the valid, and then also your standard deviations in all your directions. So you got 6 out of 6. Now click the green check mark. There you go. All right, so let's run through. Everybody get a turn. Who's next? What's your name?
Juan.
All right. So pick everything up, right, and just move the whole system to another point somewhere. And feel free to get on the sidewalk too. You know, that's perfectly permissible. All right, now you want to set it down so all 3 points are down, and then grab both of these like this and squeeze hard with your thumbs. And now adjust it so that that bubble is right in the middle. Remember, if you're moving it, you must be squeezing as hard as you can. And actually, the skill in this is how to let go softly, such that you don't, jar it out of plumb and level. All right, so that's good. Now press the S button at the top to store this point. All right, so these are your standard deviations you're getting. So those are very good. And then you store the point. All right, so let's everybody run through once, and then we'll, feel free to spread out. You know what I mean? If we were doing a national project here, we'd want to get maybe the elevations of those stormwater inlets. Right? Spread around here. Maybe some sidewalk elevations. Because when we're done, we're going to export these data, and then I'm going to go put up GIS on the projector, and we'll actually see these points we just put in.